Hey everyone, and welcome to the summer session for Intro to Earth Science. I just want to give you a brief introduction to myself and the class. My name is Stephanie. Don't bother trying to pronounce my last name. It's pretty impossible. So I'm going to be taking you through the textbook this semester. It is going to be pretty challenging. We have a lot of information to cover in just 6 weeks. So you really need to stay on top of the homework and the readings to make sure you keep up, especially since a lot of the chapters build on previous chapters. So if you start to fall behind, it's really going to make it difficult for you to catch back up and understand what's going on. Because it's an accelerated class, there is no research assignment like I usually do, so your grades are just going to be based off homework. 2 exams. You're going to have basically a midterm exam at 3 weeks and then your final exam at 6 weeks, and then discussions. You're going to have weekly discussion posts in the forums that you are going to have a prompt for. I expect everyone to write an insightful post based off that prompt, and then for everyone to, comment on at least 3 of their classmates' posts. Originally, when I did this course, I was trying to do a live stream that people could tune into, but we faced some challenges with that. There was a significant lag, making it hard for me to address questions when students had them. I would have already moved on in the material by the time it would show up. So because of that challenge, I am open to the idea of maybe doing like a weekly Skype or a Google Hangout call where any students who want to tune in and ask me questions or kind of do a group discussion, we could do that. So if people are interested in that, I'm going to maybe schedule the first one for this Thursday to kind of go over material before the end of the week, so that way if anyone has questions before the homework's are due, we could do that. And I'll post a link to that later on. So we are going to dive right into this semester. Let me grab your first chapter slides. So the first chapter, we're going to talk about matter and minerals. These are the building blocks of everything else we are going to discuss in this class. This is the foundation for essentially everything in our world, at least in the non-organic side. That's what we're going to be focusing on here. So minerals are the building blocks of rocks. All rocks are comprised of minerals. So we really have to understand minerals and their properties to be able to further understand rocks and their properties before we can start to understand the earth itself. So a mineral for this course is a naturally occurring inorganic solid with an orderly crystalline structure and definite composition. Okay. So these are terms you're going to need to remember. Naturally occurring, inorganic, orderly crystalline structure, and a definite chemical composition. Naturally defined means that they are formed by natural geologic process. Synthetic materials, so those created in the lab, are not minerals. That's why you'll see a lot of jewelry, they're called gemstones. They'll never be referred to as a mineral because they were created artificially. Solid substance means that minerals are solids within temperature ranges normally experienced at Earth's surface. For example, ice is actually considered a mineral because it is found in a solid state in temperatures that naturally occur on Earth. However, the liquid form and the gas form are not minerals. Mercury is an exception. It is a mineral that is liquid at Earth's surface. When we talk about orderly crystalline structure, this means that the atoms are arranged in an orderly repetitive manner and results in regularly shaped crystals. So basically, if I have a piece of quartz, I know that the crystals the atoms in quartz are always going to be in a tetrahedral form. And throughout the entire crystal, all the atoms are in a tetrahedral form. And any piece of quartz I find anywhere on Earth is going to be exactly the same when it comes to that. And that will never change. Naturally occurring substances that do not have this are not minerals. For example, volcanic glass, also known as obsidian, is not a mineral. It has a very non-crystalline structure. It's a very random arrangement of the atoms within the rock. When we talk about well-defined chemical composition, we mean the chemical formula for a mineral. So minerals are compounds with specific chemical formulas. I mentioned quartz earlier. Some of you may know there are a variety of colors of quartz. You've got your clear quartz, your rose quartz, your smoky quartz, your amethyst that you see a lot of times. That's actually a purple quartz. These color changes, are due to impurities, so atoms for different elements that were trapped during quartz crystal formation. But it's so low in percentage that it doesn't have an impact on the overall crystal structure, and it's so low in percentage that it actually doesn't change the overall chemical composition of the whole mineral. It just changes portions here or there, just enough so that it impacts the way light is reflected and refracted through the mineral. And finally, they are inorganics. So crystalline solids such as halite or salt are found naturally in the ground and are considered minerals. So halite is a mineral that we use with our food. It has a defined crystalline structure, and it is found in nature. Sugar, however, is a crystalline structure that we use with food, but it comes from an organic source. Okay, this comes from sugar cane, sugar beets, any of those sources. So because it has an organic source, it is not a mineral. Whereas halite has an inorganic source. It's usually an evaporite of salts from water. So just to review, what are the defining characteristics of a mineral? Like I said, naturally occurring. They are an inorganic solid. They have a defined structure and a definite chemical composition. So then what is a rock? I said rocks are made up of minerals. So a rock is a solid aggregate of minerals. So a solid mass of minerals or mineral-like matter. This means that the minerals retain their individual properties within the rock. So if you look at a rock close up, you will see individual grains of separate minerals. Whereas if you looked at something like the volcanic glass obsidian, that is minerals that have been heated, melted down to their basic form, and so there's no defined mineral structure within it. Rocks have defined individual grains of minerals within their body. So for example, here is a piece of quartz, or I'm sorry, a piece of granite. You can see some of the light pink are quartz, the darker minerals are hornblende, and then some of the more salmon colored pieces are a mineral called feldspar. So you can see very defined grains of each of these within your granite rock. We talked about minerals having a defined crystalline structure. So to understand these crystalline structures, we need to really go back to our basic chemistry and discuss the actual atoms that build our minerals. So minerals are a collection of elements, and elements are composed of atoms. Minerals are composed of elements, and rocks are composed of minerals. So here's our hierarchy. The most basic form are our atoms that bond together to create an element. These elements then bond together to create your mineral, and your minerals then either create together through some sort of temperature differentiation or lithification and compaction, which we'll get to later, to create a rock. So an element is a substance that cannot be broken down into simpler substances. There are more than 118 elements. 92 to 98 are naturally occurring, and the rest are man-made. An atom is the smallest particle that cannot be chemically split that exists as an element. So an element is a substance that can't be broken down anymore into individual components on a chemical level. I mean, we can break an atom down, but not chemically. So this is just a review of the periodic table of elements. A lot of what we're going to be focusing on are silicon and oxygen-based minerals for our more felsic ones, and then our more mafic ones are going to be more iron and magnesium based. So these elements are ones that are made in a lab. They are not found in nature. So these elements would not show up in any sort of mineral or rocks that we would find in existence. Additionally, the rare earth metals are extremely uncommon in solid earth and in geology. However, rare earth metals are actually what are used primarily in your phones. They're also used in automobiles, engines, medical devices. There are very few mines that actively collect these metals because they are so uncommon on Earth. So they're common in the Earth's crust, but rarely in mineable concentrations. And then the ones that are found are primarily in igneous rocks. There was actually only one rare earth mine in the U.S., and they have since gone out of business. China has the largest number of rare earth mines in the world currently. So, to understand how these mineral forms, we need to understand the structure of atoms and how atoms interact with each other. So, what is an atom? An atom is composed of three things: protons, neutrons, and electrons, right? Flashbacks to chemistry. So, in the center of the atom is the nucleus. The nucleus contains protons, which are positively charged particles, and neutrons, particles with zero charge. The electrons then orbit the nucleus in a cloud of negative charges. The atomic number is the number of protons in an atomic nucleus. Okay, so helium has an atomic number of 2. That means there are 2 protons in every nucleus. In every atom, the number of electrons is equal to the number of protons. Your atomic weight, or your mass, is the number of protons plus the number of neutrons in a nucleus, okay? Your atomic number is just the number of protons. Your atomic mass is the number of protons plus the number of neutrons. So helium has an atomic number of 2 because it has 2 protons, and an atomic weight of 4 because it has 2 protons and 2 neutrons. Talked about the electrons that orbit in a cloud around the nucleus. These electrons actually orbit in what are called energy levels or shells. These surround the nucleus, and electrons in the outer shell are involved in chemical bonds. These are what are called the valence electrons. These are the electrons that are really what are enabling atoms to attract to one another and form elements or to form compounds. If you all remember back to high school chemistry, the octet rule said that atoms tend to gain or lose electrons until they are surrounded by 8 valence electrons. So atoms really want to enter into a state of stability where they have 8 atoms in their outermost shell. And they're going to attract or dissociate to reach that stage. Whoops. So here's just an example of the octet rule. So atoms combine to have stable arrangements of a noble gas, or 8 electrons in the outer shell. So you may remember doing dot diagrams for these. So hydrogen has 1 dot, it has 1 electron, and that's it. So it's got 1 electron in its valence. Argon is a noble gas. It has 8 electrons in its valence shell. Oops. So, to reach this stage, there are 3 different ways they can bond. You can have an ionic bond. This is where electrons are transferred from one element to another. This is where metals bond to nonmetals. So here we've got sodium bonding to chloride to get salt. So sodium actually loses an electron to the chlorine atom. And then the chlorine atom has a stable outer valence of 8, and the outer valence of sodium loses that electron. Covalent bonds are where electrons are shared. So here we've got 2 hydrogen atoms, and what they'll do is they will actually share those electrons to try and reach a stable form. And then finally, metallic bonds are where the electrons are actually free to move between the atoms. So here we've got oxygen and 2 hydrogens, and when they bond, they've got Oxygen brings up to 8 in its outer shell, but of those 8, 2 are free to move around each hydrogen atom too. So oxygen can simultaneously have 8 electrons, while the hydrogens can each have 2. So here we've got your metal, your sodium, losing 1 electron to your chlorine. So it brings that outer shell of the sodium down to 0. So that shell is essentially non-existent anymore. And it brings that outer shell of chlorine up to 8. So then what happens is sodium lost an electron. So it is now positively charged, right? So if you have something that's neutral and you lose a negative, you end up with a positive. And chlorine gained an electron, so now it is negatively charged. So then ions with opposite charges stick or bond together ionically, as in salt. So this just is another example to go through, showing the loss of the 1 electron from sodium to chloride and how it creates the atoms. So halite, which is the name we give the mineral that is comprised of sodium chloride, has a cubic crystalline structure because each sodium ion and each chloride ion in a salt molecule are attracted to the opposite ion. So this results in a cube shape because it takes a very one-to-one pattern. So chloride, sodium to chloride, sodium. I will post this link on your week 1 because I don't think this one actually made up there, but it's just a video example of some ionic bonding. So what are the particles that make up an atom? Your proton, your neutron, and your electron. Why and how do atoms bond? Okay, they want to reach a stable configuration of 8 valence electrons, and they can bond through ionic, covalent, or metallic bonds. Okay, now we need to talk about the properties of minerals, because based on their composition and their crystalline structure, they can all have different chemical and physical properties. So first we're going to review the physical properties, because this is primarily what scientists use to identify minerals in the field. So the first one is the crystal shape. The crystal shape is an external appearance that is determined by the internal arrangement of atoms. So halite has a cubic internal atomic structure. So if halite is allowed to develop freely without any physical constraints, it will develop in a cube shape. However, this is often interrupted because you have many minerals that are developing at the same time, so there's competition for space. They don't have infinite space to develop in, so you'll often have constraints of rocks or other bounding materials, keeping them from having that perfect crystalline structure. The most common crystal shapes are bladed, so they look like very fine, thin blades, prismatic, banded, cubic, which is not shown, columnar, hexagonal, and botryoidal or globular. Botryoidal and globular actually look like there is no internal structure, but there actually is a defined structure within there. So it's important to note that although this looks like it may be non-crystalline, it actually is. Luster is the quality of light that's reflected from a mineral surface. This usually comes in pretty handy. It enables you to quickly identify what group of minerals something might belong to. You can have metallic, submetallic, glassy, dull, earthy, silky, pearly, and waxy finishes. Sometimes it gets a little difficult to tell the difference between the two. One person might say something's silky, another one might say it's pearly, and someone might say, well, this one's earthy, but it looks dull to someone else. So to a certain extent, these are a bit subjective. Metallic is metallic, and glassy is usually pretty easy to identify. Pearly can be easy, but it's a bit of a spectrum that people don't always agree on. Ability to transmit light is another property. So opaque means that no light is transmitted. Translucent means you can have light but no image. And transparent means, light and image is transmitted. So the image on our right here, it's a poor example, but this is a sample of calcite. And by this picture, you would probably define it as translucent. It doesn't look like images would transmit through it, but we'll find out later on that images actually transmit through calcite very easily. So this would be considered a transparent mineral. I mentioned color earlier when talking about quartz. This is very rarely reliable as a diagnostic because just a few amount of inclusions can completely change the color of a mineral. So what scientists use instead is what's called a streak. This is the color of a mineral in powdered form when dragged across an unglazed porcelain plate. Okay, so one of the tests a lot of scientists will do, it's called a streak test. And as you drag it along a plate, you can actually end up with basically a scratch of that mineral that is a more it's a more reliable form of identifying. You can have what looks like a gray mineral, and when you do scratch test, it'll actually have a red streak. So that makes it easy. If you have like 4 gray minerals in front of you and one has a red streak, you know it's going to be in a certain class as opposed to one that has a gray streak, which makes this a much more reliable method of identifying a mineral based on color than just the appearance of the mineral. Another one is hardness, or the resistance of a mineral to scratching. Now, scientists use what's called the Mohs scale. This is a relative hardness ranking. So on the Mohs scale, it ranges from 1 to 10, with the softest being talc, which is easily crushed between your fingers, to diamond, which is the hardest known mineral on Earth. And along the scale, some benchmark minerals are gypsum, calcite, fluorite, apatite, orthoclase, quartz, topaz, corundum, and diamond. And they're each assigned a number. So if you have something that is scratched by quartz, but it can scratch orthoclase, it's going to be considered a 6.5. In addition, we have some standard household items that help. So a fingernail, if a fingernail can scratch it, a fingernail has a hardness of 2.5. So if a fingernail can scratch it, it's probably, in the gypsum to talc range. A penny has a hardness of 3.5. So a penny will scratch your calcite. Glass has a hardness of 5.5. So a glass will scratch apatite but not orthoclase. And then steel, a steel file has a hardness of 7. So it has a hardness equal to quartz. And these are, again, really good identifiers of minerals. Finally, cleavage, which is the tendency of a mineral to break along certain planes of weak bonding. So we break cleavage down into 4 different directions. The first is when it cleaves in just one direction. So in other words, it breaks off in sheets. Muscovite and biotite are good examples of these because you can break it off into very thin sheets. Cleavage in 2 directions at 90-degree angles. So you'll have a break that has a very defined corner on one side. And this is a good example of this is feldspar. It'll have that really defined corner on one side, but not anywhere else. You'd have cleavage in 2 directions, not at 90-degree angles. So you're going to have that really defined corner, but it's going to be slightly more open. Hornblende is a good example of this. Cleavage in 3 directions at 90-degree angles. This is where you get your cubic minerals, so like your halite, your galena. And these are going to be very if they're allowed to grow naturally, they're going to be perfectly cubic in shape. Cleavage in 3 directions, not at 90-degree angles, so it looks like a really well-defined rhombus shape. Calcite is a good example of this. Finally, cleavage in 4 directions is where you get a mineral that looks like 2 pyramids stuck together at the base. And fluorite, when found in nature, is an extremely good example of this. Now, fracture seems like it might be the same as cleavage, but it's actually a different set of properties. So this is when a mineral has bonds that are equally strong in all directions. Quartz is a really good example of this. Quartz is formed by a silicon-oxygen tetrahedron, and the bonds are the same strength all the way around. So what happens is you get irregular fractures with uneven surfaces. Quartz can get conchoidal fractures, which resemble broken glass. So if you break a piece of quartz, it's actually going to look kind of like if you broke like a glass ball. And then you can also get splintery or fibrous fractures. Finally, another property are specific gravity. These aren't used as much in the field. You need laboratory equipment to really get an exact measurement on these. But this is the ratio of a mineral's weight to the weight of an equal volume of water, and it's used to describe density. So borax and kernite have a specific gravity of 1 to 2. They're very lightweight. Halite, gypsum, quartz, fluorite all have a range of 2 to 4. These are pretty average rate specific gravities. Your heavyweight minerals might be hematite or pyrite. These are going to feel much heavier in your hand than you would expect. And then extremely heavy examples such as galena, which is the mineral we extract lead from, cinnabar, which we extract copper from. These are going to look very, very heavy in relation to their size. Additionally, there are some less common properties such as taste. Halite and gypsum are going to be very salty if you lick them. Elasticity, how much you're able to manipulate them. Malleability, gold is very malleable. You can manipulate it very easily in your hand. Magnetism, magnetite and hematite are both minerals with magnetic properties. Double refraction, up here is a piece of calcite. When you put calcite over an image, you will actually see it refracted and doubled within. So as you look down through it, you're going to see 2 copies of whatever it's laying over. And then effervescence. Calcite will effervesce when you put hydrochloric acid on it. So your calcite can look very similar to halite and can look very similar to anorthoclase. They're all white minerals. They all have very similar structure. If you drop hydrochloric acid on them, calcite is going to fizz like you see in the picture here, and that's the only one that will do it. So halite tastes salty. Talc feels soapy, so it feels a little like waxy in your hand. Gold is malleable. Like I said, magnetite is magnetic, and calcite effervesces. So I'm going to skip over this. This is just a review of what we just covered. So these are really the properties you're going to want to remember moving forward. There are 8 elements that compose most of the rock-forming minerals on Earth. Oxygen is present in 46.5% of all rock-forming minerals. Silicon, 27.7%. Aluminum, iron, calcium, sodium, potassium, magnesium. These are the primary elements that you're going to find in any mineral found in any rock on Earth. Now, silicate minerals are the most common group. They actually make up more than 90% of the Earth's crust. So most of the Earth's crust are made up of silicate mineral rocks. They crystallize from molten materials such as lava, and they contain characteristic molecules, the silicon-oxygen tetrahedron that I mentioned earlier. So this happens when you have a silicon atom, and that is bonded equally in all directions to 4 oxygen atoms. Now these tetrahedrons can then combine into what are called chains. So olivine are single units. These tetrahedrons do not develop or attach into any sort of chain formation. Each tetrahedron is its own unit. The pyroxene group of minerals, such as augite, develop into what are called single chains. So you'll have the alternating direction of the tetrahedrons. Then the amphibole groups are what are called double chains. You'll have 2 single chains that are attracted to each other, creating a double chain, creating a very uniform sheet. So micas are just sheets of multiple chains attracted to each other along one plane. Feldspars and quartz are 3D networks. So they're not chains or sheets. It's actually the tetrahedrons attracting to each other all the way around in 3D space, whereas previously we've been talking about a 2-dimensional attraction. Silicate minerals are the light-colored minerals. The most common silicate minerals are feldspars, quartz, muscovite, which is the lighter variant of mica, and clay minerals. They can also contain varying amounts of aluminum, potassium, calcium, and sodium. Feldspars, like we mentioned, these are the most abundant. They are found in igneous, sedimentary, and metamorphic rocks. And like we mentioned before, they have 2 directions of cleavage at 90-degree angles. Feldspars are a 6 on the hardness scale. There are actually 2 different types of feldspars, your potassium feldspar and your plagioclase feldspar. Your potassium feldspar contains potassium ions. So potassium feldspar is also known as orthoclase. Your plagioclase feldspar contains calcium or sodium, but it also has striated cleavage surfaces. Okay, so it's not a very uniform cleavage surface. So sodium-rich plagioclase is an albite, which is very white. And then a plagioclase feldspar that has striations is what gives us the mineral or the lab-produced gemstone labradorite. So if you've seen granite countertops where it kind of has that like sheen where it changes colors at different angles, that's the labradorite or the plagioclase feldspar in the countertop. Quartz is common in all three rock types, and like I said, impurities cause a variety of colors. Quartz is a 7 on the hardness scale. It forms hexagonal crystals with pyramid-shaped ends and fractures conchoidally, or the smooth shell-like curves that's very glassy in appearance. Now, the dark-colored silicate minerals contain iron and magnesium. These are heavier than the lighter-colored and contain minerals such as pyroxenes, amphiboles, olivine, biotite, and garnet. The dark color and the higher specific gravity is typically because of the high iron content within them. Yeah. Olivine is one of the major constituents of the darker igneous rocks. It has a black to olive green color and a glassy luster, and is extremely abundant in the upper mantle. Okay, so not on the surface, but right below the crust in the upper mantle. Pyroxenes are important. Also, they have, one of the most common is augite, is very black and is opaque. And then it includes minerals that commonly make up the darker portion of light-colored rocks. So hornblende is a dark black mineral, but it is commonly found in lighter-colored rocks, such as the granite we saw earlier that had the quartz and the plagioclase, both the light silicate minerals. But the hornblende develops kind of right behind them on the Bowen scale, and so you'll commonly find it with those lighter-colored minerals. So here's an example of olivine-rich peridotite. Here's an example of hornblende. You can see the striations on it, the dark color, and augite. Now these are all that we talked about are silicate-based minerals. Now there are non-silicate minerals. They're not as abundant. They only comprise 8% of Earth's crust. They're often constituents in sedimentary rock. And these are important for metal ores and construction material. So salt is a non-silicate mineral, the sodium chloride. It is an evaporite. It's an evaporite. Same with calcite and gypsum. These form within heated hydro systems, the warm groundwater, and these precipitate out as it moves through typically sedimentary rock units. Pyrite and galena are also those that form through hydrothermal areas. Pyrite is copper-rich, and galena is what is mined for lead ore. So some common non-silicate minerals: calcite, dolomite, which is very similar to calcite, but some of the calcium has been replaced with magnesium. Halite, which is our salt. Gypsum, which is a type of evaporite and salt. Hematite, magnetite. Galena, like I mentioned, is a lead ore. Chalcopyrite, it's a lot of copper. Typically forms in conjunction with galena. And fluorite. So the non-silicates are broken down into 6 major groups. You have your oxides, which are your hematite, magnetite, corundum, and ice, because they all have oxygen, O3 typically, but oxygen compounds. Your sulfides, which are those that are formed with sulfur, so your galena, which is a lead sulfur, sphalerite, which is a zinc sulfur, pyrite, iron sulfur. Chalcopyrite is a copper and iron sulfur, and cinnabar, which is, I forget what Hg stands for, sorry about that. Mercury sulfur. Additionally, you can get gypsum and anhydrite and barite. These are sulfide compounds, so the SO4 compounds. Your native elements, like we talked about, your gold, copper, diamond, these are single element minerals. Halides, or your salts, so halite, fluorite, sylvite. And then your carbonates, calcite and dolomite, so it's compounds of the CO3. So calcite is CaCO3, and dolomite is calcium, 1 calcium, 1 magnesium, and then 2 of the CO3. So these are the primary ones we'd be looking at. Carbonates are the primary constituents in limestone and marble. And limestone is used for roads, building stone, and is the main ingredient in cement. Halides are found in sedimentary rocks, typically in thick layers, and are frequently mined for human consumption or additives. Other of these non-silicates have value. Hematite is mined for the iron, sphalerite for zinc, galena, like I said, for lead, copper, and gold, silver, platinum. And for example, most of these ores are actually used in for money, but some ratio. So the mineral resources are found in reserves. These are deposits from which the minerals can be extracted profitably. So for example, there's some salt mines in New York at the tips of the Finger Lakes. So those are considered halite reserves or salt reserves. When we talk about an ore, these are metallic minerals that can be mined at a profit. So reserves are deposits of minerals such as halite, fluorite, whereas ores are specific to the metallics, so gold, silver, copper, lead, that can be mined at a profit. So the different mineral groups are the silicates and the non-silicates. And just a little bit of geology joke. Okay, manganese are a rock. How sweet, my birthstone. So that is it for minerals. I'm sorry, that was a very quick video. So please contact me if you have any questions about that. But I hope that kind of gives you a feel for the course, how we'll go through this. And like I said, I will try and schedule kind of an Ask the Prof video chat if you all want. And don't hesitate to email me if you